5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Pixxel is a prominent Earth observation startup originally from India and now present in the United States too. They are focused on so-called hyperspectral imaging. Founder and CEO Awais Ahmed is our guest this week. Enjoy.
My name is Raphael Rodkin. I'm the founding partner of E2MC, Earth to Mars Capital, a venture capital investor in dozens of space startups worldwide, among other roles I have, such as being a part-time podcast host. Just as a reminder, this podcast is for informational purposes only. It does not reflect any view by E2MC, and nothing should be taken as investment advice. Before we start, a quick favor. If you do enjoy this podcast, please leave us a 5-star review on your favorite podcast app, such as Apple or Spotify. It does help other people find the podcast. Now on to today's episode.
Hey, space enthusiasts, welcome back to another episode. Very excited today because we have another startup that's originally from India, and longtime listeners or people who follow my work at E2MC know we're extremely bullish on India as a space ecosystem. So our guest today is Awais Ahmed, and he's the CEO and co-founder of Pixxel. Welcome.
Thank you, Raphael. Great to be here.
Yeah, thanks for doing this. And so Awais, the way we usually start this is with like a short elevator pitch for those listeners who don't know who Pixxel is yet.
Yeah, so sounds good. I mean, in a nutshell, what Pixxel is we are a planetary intelligence company. What that means is we build, design, launch, and operate our own constellation of imaging satellites. These satellites capture phenomena happening around the globe. We beam those images down and we sell the imagery and the analytics that comes from those satellites to organizations in the agriculture industry, for example, where we can help reduce the amount of wastage from crop diseases, or to companies in the oil and gas industry, where we can help detect when leakages are occurring in oil and gas pipelines, to the mining industry, where we can help identify critical minerals, to identifying the impact of the mining operations on environment and so on. So what separates us from rest of the satellite imaging companies is that we focus on hyperspectral imaging. When we started, there were already quite a few companies working on satellite imagery, but they all provided either visible or multispectral imagery, which is either 3 wavelengths of light that human eyes can see, or at best 8 wavelengths of light. Now, that wasn't enough to be able to see some invisible problems, and that's where hyperspectral came in, being able to see hundreds of wavelengths, in our case, more than 250 wavelengths of light, contiguous in nature, so that we are not missing any part of the electromagnetic spectrum. So what we're doing is building a health monitor for the planet through a constellation of our own hyperspectral imaging satellites.
Terrific. And so when you said we'll delve into some of the technical stuff on a higher level later on, but just quickly, you mentioned the 3 bands that the human eye can see. Is that like the famous RGB, like the red, green, blue?
Exactly.
Okay.
Yeah, red,
kind of
green,
stuff
and blue.
like where your color TV kind of puts the pixels together and
Exactly. Yeah.
okay,
Yeah.
cool. Yeah, we'll delve into that later on. But like you mentioned, there have been sort of a bunch of, remote sensing Earth observation is arguably one of the oldest space applications, right? Sort of probably from spy satellites starting in the 1960s or so. And you mentioned there, even in this what we call now new space, there have been companies that started sort of 2010, 2011, 2012. When did you guys start? When was Pixxel founded?
We started in early 2019, February, March to be precise. My co-founder and I were still in the final year of our undergraduate studies, but yeah, early 2019.
Okay, cool. So that was starting to be like an exciting time in space, right? Probably not as exciting as now. Space keeps getting more exciting, but even in 2019, like SpaceX was already like regularly landing like first stages and things like that. So what and your studies were in aerospace engineering or a related field?
No, I was doing studies in mathematics. That was
Okay.
my degree.
That's what
But
even smarter people.
so there was a student satellite team though at college that I was a part of. So that's where I got exposure to the intricacies of working on satellites. But yeah, no, the coursework and the degree was on mathematics.
Okay, well, that makes my next question even more justified. Sort of like what? So it was an exciting time in space already. I don't know how much that was also visible in India already, but if it was a student satellite team, then probably it was. That what led you and your co-founders, like what led you personally to start this?
Yeah, I think a few factors, right? I think the first boils down to the obsession, I would say, with space. Ever since I was a kid, like most kids, I was also very fascinated with looking at the night sky and trying to get access to telescopes and just finding out what's out there. And that obsession or passion never really left, even when I entered college. So as soon as I got to know that there was a student satellite team at the university, in the first year, I was like, yeah, I have to be a part of this. And it was a long drawn process. You had to write an examination. They would select a few of them, and then you had to go through a 3 month study period or a probation period of sorts, after which you had to write one more exam on what you've learned, and then you got into the team, because they only wanted to get folks that were serious about actually learning and working on the satellites. And the good thing was, once you got in, you were trained by the scientists at ISRO that were guiding how you go about designing a satellite. So I think that really taught me what goes into work building the hardware that is needed to work in space, and it was like really fascinating. Got to learn a lot in my first and second year. And the other final thing I think that ended up crystallizing and working at Pixel was I was one of the founding members and engineering leads at the Hyperloop India team. Now, this was around the time Elon Musk was tweeting about traffic in LA, and he wanted to test out if the Hyperloop concept could work, which later morphed into the Boring Company. But at that time, it was SpaceX that decided that they would build this 1 mile long vacuum tube near their headquarters and put out a challenge to the teams around the world, come race here. We thought it was a good chance to meet Elon, so we decided to just apply for the sake of it. And thankfully, to our pleasant surprise, we got through the first stage. So now we had to take it seriously, and we kept getting through the successive design stages. And out of 2,500 or so global applicants, 20 were chosen as finalists, and we were one of them. And so we had to build this Hyperloop pod in India. We took it all the way to Los Angeles, presented to Elon Musk and the rest of the SpaceX team. So while we were there, they took us on a tour of the SpaceX factory. And as you said, at that point in time, they had already started landing boosters. So they had the first booster to have landed back kept right in front of their office, which still exists in Houghton.
Yeah.
And that was kind of like a crystallizing moment for me, or a eureka moment for me, that I've always loved space and have done things in the student satellite team and all of that. But I want to work in space technology for the rest of my life. So came back into college. I was finishing my third year, entering the final or the fourth year. And that's when I decided that let's look at what's out there. Can we build something of our own? And seemed like there was a gap in satellite data with hyperspectral. No one was doing it commercially. So I think that's really what led to us then saying, I think it makes sense to build our own satellites of hyperspectral imaging, because we couldn't find anyone providing that data on a regular basis.
Oh, interesting. So it was almost like some sort of like systematic process you went through, sort of like you decided you want to do something in space, but then even within space, and you had some, clearly from the sounds of it, between Hyperloop and the students group, some like hands-on engineering hardware experience, right? But even on the upstream hardware side, you could have done anything from like, building a launch vehicle, as some fellow founders in India obviously are doing, to building just satellites themselves, to building like, specialized remote sensing payloads, to building communications payloads, to other stuff. So you had
Yeah.
like, so you systematically narrowed it down to hyperspectral from the sounds of it.
I wouldn't say systematically, but I think after a certain point, common sense led us to finding a gap that was begging to be filled globally, right? So I think a few factors led to why we chose hyperspectral. One, there were already some other companies doing launch vehicles, right? Globally, we talked about how SpaceX was already like much further ahead. You had the likes of Rocket Lab, and you had Astra and a few others, Firefly, all still at that point in time fairly well known, doing rockets globally. And even in India, we already had Skyroot and Agnikul, who had started about an year or a year and a half ago or 2 years ago. So we didn't really want to either replicate what was already done globally just in India. We really wanted to build something that could truly be global. So I think that kind of left out the launch vehicles. SpaceX was already starting to, launch the earlier of the Starlink satellites, and you didn't want to compete with Starlink on anything
Mm.
telecommunications, and it requires many billions of dollars, if not hundreds of millions. And so we decided we didn't really want to, one, compete with SpaceX at the stage we were at, and second, something that required literally billions of dollars. Maybe we wanted to look at something that would be, that could be proven in tens of millions of dollars instead of hundreds or billions. And I think there was also thinking about where this would lead to in 10 years or 15 years or even 50 years. And the capability or the internal expertise of having to build satellites led a direct line towards building spacecraft for Moon, Mars, the rest of the planetary system exploration. So I think we wanted to really focus on a global gap like hyperspectral that no one else was doing, and and become the best at it globally. And second, it didn't require humongous amounts of money like launch vehicles or comsats, etc. required. And the third was, I think it was a direct line of sight to what I personally wanted to do in the long term, scout asteroids, mine asteroids, scout what's out there in the planetary system. But that's like much further ahead. It was just like, let's build this unique thing that no one else is building for the Earth today.
Okay, and as you started thinking about hyperspectral, I mean, I think back in 2019, that was still like a relatively esoteric thing. I mean, there obviously were some, like science and government satellites out there, I assume, with that capability. But how did you get comfortable with that there would be market demand and sort of like where did you see you mentioned in the intro some of the use cases that you have now, like agriculture and oil and gas and mining,
Yeah.
but how did you get comfortable with that? And sort of was there something that you guys thought that was like a aha moment, sort of like, okay, no, those guys, they really should need it and we're going to target that market?
I don't think there was one particular aha moment, but there were a smaller set of aha moments that kind of led to it. I think we just explored all kinds of satellite data that was out there, right? And we ended up landing on hyperspectral and ended up seeing that there's not as much of that data that's available, especially commercially. I think what gave us comfort was, I think, a few things. I think we saw that there were few research articles that were already out there that was on either the NASA data or the Avaris NG data that NASA collected through their drones. So it wasn't completely like a new thing. People had worked with hyperspectral through drones and airplanes specifically, and some recent satellites had gone up that proved that the concept was viable. It just seemed to fit into that curve where in the 1990s or 80s it was still just panchromatic imaging, which was black and white.
Hmm.
Then it progressed to RGB imaging, which is color imaging in three wavelengths. And then in 2010 or so, you had the SkySats and the planets who delved into multispectral. SAR came into being. We saw that hyperspectral could likely take a similar pathway. Yes, it's esoteric now, which is in 2019, but all we needed to do was build it at the level of specs that the customers are willing to pay for. The
Hmm.
the easier thing I think that kind of justified it was hyperspectral is a superset for multispectral. What you can do with multispectral, you can still do. So you can still sell to the same customers and the market already existed for that.
Hmm.
But beyond that, since it's a superset, now you can do three, four, five more things. And that's where the value, I think, started to become a little bit evident. But more importantly, in the early days, I just sent out some LinkedIn in-mail messages and some cold emails to customers or companies that were already doing hyperspectral analysis. They were either doing hyperspectral analysis from lab collected data or
Hmm.
from drone collected data. And these were everywhere from the big companies to some small startups. And thankfully, about 90% of the folks we reached out to replied through for a cold message or an email. And all of them said, if you're able to provide hyperspectral data at XYZ specs, we would buy hyperspectral and we would be even willing to pay you a premium. That kind of gave a little bit of confidence that, okay, one, we could see a trend like has happened with SAR and with multispectral. No one else is doing it, but that's where it could go. But only, you need to get the specs right. And then we confirmed that with actual customers who would end up paying later. We realized that, okay, there seemed to be some amount of pent up demand in each of these industries. There was no way of being completely confident whether that would be a large market or whether it would really scale or
Hmm.
whether we could get there. But it was just that spark that we needed to say, let's go try it out. Why not?
Okay. And so now, when six years later after the founding of the company, what are the use cases you think you're most excited about actually for the commercial market? Let's leave the sort of government
Yeah.
intelligence use to one side for the moment.
So I think the ones that I'm excited about are predominantly in the carbon credits and the carbon sequestration and the sustainable space. But the ones that we have the most number of customers in and where we see a lot of growth are in the agriculture space, right? So I would say it is in the spectrum of agriculture and environment where the use cases are very similar, but the companies are quite different. For the environment, it's either carbon credit companies or NGOs or some government agencies. For agriculture, it's proper agri companies. Either they make seeds of their own, or they have farms that they manage of their own, or they sell fertilizers, or they are commodity trading companies. All of them need to know what's happening at different parts of the growing season. Then you have some mining companies, not a lot today, but they're at least starting to pick up where in multiple continents they want to identify critical minerals for the EV transition, cobalt, lithium, and many others that
Mhm.
Hyperspectral can help detect uniquely. And then you have the oil and gas companies where we can detect underground oil leaks and above ground methane leaks or other greenhouse gas leaks, which either only GHG specific satellites can do for methane or Hyperspectral can do for methane, but also other gases and oil as well. So I would say agriculture, oil and gas, mining, and environment are the big ones that we focus on today. The most interesting and the more novel ones are finding out the exact amount of carbon being sequestered and the amount of biomass that's present there, because that's new, that really hasn't been done at scale and accurately before. But the one that's most established and where we see the biggest demand is agriculture.
Okay, we could probably spend hours just talking about each single one of those, but I mean, just in no particular order, picking up on some of the use cases there. So something like mining, so it sounds like it helps to identify deposits. So can it actually penetrate a certain level below ground?
It can't. No, no. It's all on surface, right? So
So far,
hyperspectral
yeah.
can't
Okay.
penetrate. But usually most metals or minerals have either some presence above ground, so you can detect the presence of it, but you can't detect how big it is. For
Hmm.
that, you need to drill and find out how big that ore is, for example. But we can detect that, okay, we were able to detect the presence of lithium in a decent quantity in this area. Now it's still up to the company or the government to go and drill and find out how big the ore is. The second is, there are some cases where the metals or the minerals are not available, are not visible directly, but they have indicator minerals that almost always come with them. So gold almost always comes with some other indicator minerals. And so if you detect those, you have a higher probability that there's a gold ore there, while we are not directly detecting gold. So we can't penetrate anything anywhere except near the coastal areas where we can do something called bathymetry studies, but
Mm.
it's generally not a penetrative data set. We are waiting for photons to hit the surface of the planet
Yeah.
and get to us. Yeah.
Okay, and then I mean, just to pick another one, agriculture. So how should I imagine the use cases there? Is it like precision agriculture where you see the state of the plants, or like what what is the main use case there?
Yeah, so I would say it's, let's take the entire life cycle, right? Even before a seed is sown, the fertilizer companies, for example, want to know what nutrients are present in the soil and what not. Is
Hmm.
there a lack of nitrogen in this area, perhaps, or is it phosphorus or potassium? And if you can identify a nutrient map of the soil, the fertilizer company can now go to the farmer that is there and show them this data that, look, your part of the land is missing nitrogen. Here's a nitrogen fertilizer from us that you can use. And
Hmm.
usually these fertilizer companies are already selling fertilizers. They can just provide that as an add-on service to the farmers that they have, or the farmers themselves can get to know what fertilizers they need to buy from someone for the nutrient maps. Now, once the crop is sown, in Europe and in US, it's not as big of an issue identifying which species of crop it is. Every year it's the same one, and then it's very uniform and large areas. But in Africa or in India, there are these smallholder farmers, and you need to identify what species of crop is growing so you can
Mm.
more accurately estimate what the yield will be at a later point in time, so the government can either plan for exports or imports depending on whether there will be a surplus or whether there will be a lack of the amount of quota that needs to be grown. And then, especially during the growing season, we can help identify early signs of crop diseases and pest infestations. Now, the problem is usually with multispectral data, you detect something called an NDVI, but by the time you see NDVI start to change, the disease has already been in the crops for a few weeks, 2, 3 weeks, or 4 weeks, depending on which type of disease it is, or even pest infestations. It's already grown to a certain area before you can start to see the symptoms. Whereas hyperspectral, you can detect subtle changes in the spectral signature that many weeks in advance, like 3 weeks in advance. And that gives the farmers a heads up that, okay, there's a crop disease that's starting from here before it spreads to a larger area. Let me go figure that out. Or we can also identify the amount of chlorophyll content or the irrigation content, which might be signs of something else. So I think that's across the growing season. And then, as I mentioned, for governments and for commodity traders, what is the yield going to be for a particular
Mm.
crop?
Sure.
Much more accurately than multispectral would provide you.
Okay, just to open a quick bracket because we're technically a non-technical podcast. That was terribly phrased. Anyway, multispectral versus hyperspectral. Just a quick definition for our listeners.
Multispectral is anywhere between 4 wavelengths of light to maybe 20 wavelengths of light.
Okay.
Hyperspectral is 150, 100 plus wavelengths to 300 plus wavelengths of light. And the main difference is multispectral is discrete, as in the amount of data you're capturing has big
Hmm.
gaps in the spectra.
Hmm.
Hyperspectral is a continuous curve.
I mean, is it truly continuous, or are the bands getting so small that it's
It's
continuous?
obviously not truly continuous. Nothing is
Yeah.
truly continuous
Yeah.
because of Planck's length
Yeah,
at certain
okay, we're getting
point
into the maths
we can
physics.
fall
Okay,
down.
well, I get you.
So very similar to that. It's not truly continuous, but since the bands are
Yeah.
so narrow in our
Okay.
between 2.5 nanometers to 5 nanometers, it ends up looking like a very
The
continuous curve.
limits. Okay, yeah, okay, gotcha. So, I mean, you mentioned, okay, again, we have to be careful not to get too deep into maths and physics here, but you mentioned like the photons at some point in time before. So, I mean, that's a lot of bands. And then I don't know what your spatial resolution is. I mean, if you want to mention it, then feel
Yeah.
free to. But are you getting enough photons? And how are you getting enough photons? And can you, well, obviously you do, but I guess that comes back to resolution and signal noise ratio and things like
Yeah.
that. But then I guess the related question is, are your what you're doing for your customers because of that photon issue, if it is an issue, is it typically tasks, or are you also
Yeah.
kind of scanning the entire Earth and then selling the data?
Yeah, so I think you're absolutely right. The amount of we are starved for photons with hyperspectral because for multispectral the same number of photons are being split into 8 wavelengths, whereas in our case we need to capture 150 to 250 wavelengths of light. So that leaves much lesser photons per band. So we need to figure out very unique and creative ways of increasing the amount of photons per area per band, and we do that through a variety of different ways, including having to do some forward motion compensation on satellites, etc. So yes, it is a problem, but it's not a problem for most use cases because we have designed our cameras in such a way as to get SNRs that our customers can actually get to the use cases. Now, there end up being certain situations, for example, especially in extreme north or extreme south regions where the amount of sunlight might not be enough, right? Let's say we are taking an image of some area, and usually we image between 9:30 to 10:30 a.m. local time, which means when we're capturing an image, the local time at that area is between 9:30 to 10:30.
Yeah.
So that provides enough light, and the sun's already beyond a certain point. But sometimes when we are capturing images with a lot of slew, let's say 30 degrees of nadir, or trying to capture areas not exactly in the pathway of the satellite, the light conditions might not be suitable enough. The sun elevation angle might be too high where there's not enough light. So we try to filter those areas out. So all that we capture is within the constraints where there's enough light that's bouncing back. The SNR will never be as good as multispectral
Mm.
satellite or camera of the same size. But our hyperspectral satellites are sized much bigger than some multispectral satellites. So that means that we can capture a lot more photons and try to compete on SNR as well. But we don't really need to compete on SNR exactly with multispectral. What we need to compete on is, multispectral images are at 5 meter resolution. We tried
Mhm.
really hard to get our resolution to 5 meters so that there is no compromise that our customers need to do between a multispectral provider
Mhm.
and a hyperspectral provider. But now instead of having 4 wavelengths or 8 wavelengths, you have 250 wavelengths. That's where the use cases start to become really interesting for us. But yes, in some cases where there's low sunlight, but that's very minuscule number of cases, we tend to struggle sometimes with having enough signal. But mostly we have figured out that it is not a problem 98% of the cases.
And this type of special instrument payload, like the hyperspectral payload, is that something you had to develop yourselves, or was that something you could build upon?
So we looked at the market. There were a few companies that were selling hyperspectral cameras, especially for drones, and but some of them also for space, probably two or three for space. Now, when we looked at those cameras, the resolution and the quality, including SNR, was not where we needed it to be because they were designed keeping in mind like a very coarse resolution, usually 30-meter resolution to 20 meters resolution. And that wasn't good enough. When we asked customers what resolution they wanted, 10-meter was like a hard stop, and 5-meter was a hard stop for some customers. So 5 we decided will be our GSD so that we don't really have to also keep listening to the comparison that most multispectral we get at 5, but hyperspectral we have to compromise at 10. So that came from the customers themselves. And yeah, I think we couldn't find anything out there in the market that we could directly take and launch. So we had to build it ourselves. We put together a camera team that previously had built hyperspectral cameras. We said, okay, here's our specifications that the customers need. Let's design the camera on the basis to hit those specs. So that decided the size of the camera, the quality of the camera. Then we designed the satellite around that camera. So the size of our satellite comes directly as an outcome of what the customers need. Whereas in some cases, you will have seen some customers decide on a CubeSat format first.
Mm.
Then they try to cram as much of a capability into the satellite as
Yeah.
you could, which is one approach, certainly. But in our case, we wanted it to be driven by customer requirements.
So you ended up doing your own satellite.
That's right. Yeah. And the satellite was also very similar calculus. There were many more options for satellites, but they were all like standard off the shelf offerings that weren't optimized for hyperspectral. Now, the problem with hyperspectral is it's a lot more power hungry than a normal camera.
Yeah.
It has a lot more data than a normal camera, and it needs much more accurate stability of the platform than
Yeah.
normal camera. And either we could pay someone to customize these satellite buses for us, which would end up costing an arm and a leg for us at that point in time, or we said, let's build it ourselves. But as I mentioned to you earlier, also long term, we want to have the capability to build our own satellites because we can then move faster, we can iterate quickly, and then also it gives us the chance to do other kinds of satellites and spacecraft. So yeah, we decided to do our own spacecraft as well.
So, I mean, if you want to talk about it, how much did you have to end up vertically integrating, right? Because, I mean, to some extent, you were starting in 2019, so at least it was better than, I don't know, when like Planet started in 2010 or
Yeah.
something. Really, was not many places
Yeah.
they could go to, right? 2019 was a little bit better, right? But for what you're describing, I totally
Yeah.
get these technical challenges. You're like saying, okay, accurate pointing, like, did you have to kind of do your own like ACS, like reaction wheels, or like how much did you have to vertically integrate in the end?
Yeah, so I would say no, I mean we vertically integrated as much as we could without having to spend a lot on like internal R&D. For example, a camera is a very critical part of what
Sure.
enables the customers to interface with our images, and so we really needed to have full control over how that looked like, and that was non-comp that was like non-negotiable. On the satellite itself, we weren't as much of a purist as much of purists on that one. Like Starlink, for example, almost everything is vertically integrated, but they could afford to do that. When you're building tens of thousands of satellites, you can afford to spend a few millions of dollars setting up your own reaction wheel facility and your own optical communication terminals and so on. But in our case, we said, let's build only the most critical parts in-house, like the onboard computer, like the flight software, like the camera, and then the rest of the components like the reaction wheels or the star trackers and the solar panels, we just procure from other organizations. We didn't really want to do everything in-house from every component, because this market thankfully already existed fairly well. Even in 2019, it just gotten better now. Like you have 5 to 10 companies providing solar panels for space. You have 15 to 25 companies providing reaction wheels of all sizes, so we can just choose the best out of the lot and then have backups for those as well. So that's like how we do a combination of doing things ourselves, which are very critical, but then for everything else, just buy them off.
Okay, and so after all of those design decisions, what did your satellite end up looking like? Like, for example, I'm roughly speaking, how big is it?
Yeah, so for example, our demo satellites, we also decided to do it as CubeSats, like 12U CubeSat, for example, because we had to launch it quickly. And so we decided we would just work with the existing paradigm. But then our resolution was also like 30 meters for our first demo and then 10 meters for the next demo. Then for the Fireflies that we launched this year, which is the fully commercial versions of our hyperspectral satellites, which is what we wanted to get to, the size of the satellite ended up being about 60 kilograms all in all per satellite, and we built 6 of them. Now, about 10 to 12 kilograms out of that 60 is the camera itself, and then the rest of it is the satellite that makes sure that the camera does what it's supposed to do. So it ended up being around 60 kilograms and the size of a mini refrigerator in terms of volume.
Okay. And is this, let's say, something you're happy with for the moment, or would there be some like, is there some constraint that's keeping you from like something that you would consider even more optimal? I mean, I'm just like, completely like open-minded here. Like, let's say Starship was operational and you could put like some giant-sized satellite up there. Would that make any sense? Or is there something you would like to do which you can't do today?
It would. I think we are moving towards larger satellites. So, for example, the Fireflies are looking at hyperspectral data only in the visible and near infrared range. So, that's about 150 wavelengths. We are working on Honeybee satellites right now, which will expand that to about 2500 nanometers. So, a wider wavelength range, which can see more things. That is 170 to 180 kilogram satellite, right? So, it's already 3 times as
Yeah.
big in terms of its mass because the camera is bigger, because the amount of spectra you're capturing is much bigger, and it gets much harder as you go towards the later parts of the wavelength. So that's something we're already working on. And the first of these should launch sometime in the first half of next year as well. And then, there will be some other improvements we are already looking at for our version 2 of these satellites, probably in a couple of years, where the resolution will get much better and the number of bands also much better. So the satellites will always be an outcome of what quality of data we want to see. So 60 ended up being the smallest and the most optimum we could do without compromising on the current camera. 180 is what we can do with the next set of camera. Maybe we will end up being at 250 for the ones above that, but I don't think we would end up building something so big to utilize like a Starlink, a Starship yet. Yes, you could build a much larger telescope and launch it than you could with existing rockets, but it comes down to like the same approach. Do you want to build and launch many more satellites so that it works as a constellation, or you want to build one huge, pristine, exquisite satellite that costs a bomb but doesn't provide you the same level of coverage? We would rather prefer the former than the latter.
So on I mean, talking about the spectral bands, right? So like you said, we kind of gone from like monochromatic to like the 3 bands of like visible, like color light to dozens in a multispectral range to now hundreds. And it seems like keeps going up, do you think there's going to be some sort of asymptotic like usefulness limit, or is it just going to be like, it seems like with data almost that's never the case, right? I mean, like I remember I'm old enough, like my first digital camera was like 1 megapixel, and I thought like, oh, that's great. And it was like five. Oh my God, who needs more than five? It was like 10. Oh, who needs more than 10? Like now it's like, I don't know, 20 or so. But do you think there's any limit, or it's just going to keep going and we're going to discover incremental use cases?
I think there is a limit. I think we'll probably get to thousands. It's called ultraspectral. Once the sensor technology catches up, I think we are also limited by the readout speed of these detectors. They are not as fast as your CMOS detectors or something else. And even then, since your satellite is moving so fast, if you want to capture thousands, you need many more, and then it needs, improvements in the quantum efficiency of the detector, etc. So your signal to noise ratio is still better. So I would say we will definitely likely see, at least we will attempt to get to thousands of wavelengths at some point in the near future. But I don't think we will need 10,000s of wavelengths, for example. I think the innovations will be in also expanding the wavelength range, going from ultraviolet to infrared to thermal and so on and so forth. So thousands maybe, but definitely not beyond that.
I mean, do you think there's any sort of really interesting use case we haven't unlocked yet because we're not in that number of bands yet?
Yeah, I think it's like the Pareto principle. 80% of the use cases are handled by what we could do with ants and honeybees, maybe even 90% or 95%, and then you would have the remaining 5% of use cases you can't. UV images help with a lot of the other weather parameters and things like that, and thermal can sort of help with nighttime imaging and so on. So there's always more you can add, but I would say, 80 to 90% of the use cases are covered with the 400 to 2500 nanometer range. Yes, there will need to be an expansion to other parts of the wavelength, but it won't provide the same level of add-ons. It will be the additional incremental value additions.
Gotcha. Okay, and then sort of one question that's obviously intimately connected with that is because like you're generating like an increasing amount of data there, right? I
Yeah,
mean, people I think call it the data cube, right? Which I guess is sort of
that's
like
right.
position versus the timestamp versus the band. I
Yeah.
think that's what it is, right? And so like just the cube just keeps getting bigger, right? Because of the more coverage, but then also like the spectral bands as
Yeah.
we've been talking about the last few minutes, right? And then very interesting, I didn't know that, but you mentioned a few minutes ago, you guys, one of the design decisions you guys took is actually to build your own onboard computer, right?
Yeah.
Which I guess is processing
Yeah.
images. So let's talk a little bit about sort of like this, because it's obviously something we've seen on Earth, like the data explosion, right? Now it seems like a data explosion on orbit or like space in general. Like, how do you guys think about it? How are you thinking about it now? Like, how much onboard processing should there be? How much is actually feasible? Yeah, set of interesting questions around that.
Yeah, I think the amount of data that hyperspectral cameras captured was a big factor in deciding to build our own onboard computer, and that included everything from the storage to the compression we needed to do to some kind of edge computing to making sure that the entire pipeline of the camera capturing the images to storing it to there being a very smooth line of connection to the radios which are beaming down this data, because you are only as productive as the amount of data you can beam down from satellites,
Sure.
because you have a limited amount of ground station time. You can add more ground stations, but that comes with some other power budget considerations. So, to have control over what the satellites can do and especially what the camera can do, we had to build our own onboard computer and flight software, predominantly because we also had to compress without losing data for the massive number of bands you have. And it also becomes a problem in communication, like you are trying to be so power efficient that the transfer of data between even onboard storage in the camera to the onboard storage on the satellite to the radio ends up becoming a clogged point some points in time if you haven't designed it well enough. So I think we had to struggle with that. But now that things are generally getting better, the radios are getting more powerful, the compute is getting more powerful, the storage is getting larger and larger for the same amount of volume and mass. I think it's starting to become easier, but it's still much tougher than multispectral. I think we face similar issue as synthetic aperture radar, but it's even more data than SAR as well. But once it's on ground, it's much easier to manage with AWS and with the other kinds of compute sort of happening now. We just have to build these kind of architectures that enable us to work with the hyperspectral data cube, as you mentioned. So it's much easier on ground now. We have built a platform called Aurora that enables easy exploration, and customers don't have to worry about storage and all of that. But in space, you are struggling for photons not only on your camera, you're struggling for photons on your solar panels, and there are limited amount of them, and so you have to make the best use of them. And we try to be efficient, but that's where most of the power ends up going.
And so, to the extent you want to, because like you said, like there's not infinite ground stations around, and to the extent you want to handle or I guess limit some of your data by onboard processing, I mean, just what's your current quick view on sort of like the state of machine learning in orbit, like both on the hardware side as well as on the like running algorithms?
Yeah, I think so. We do some kind of novel machine learning, like figuring out if an image is even worth beaming down. Like, for example, let's say we've captured an image and it has 90% of it covered with clouds. There's no point beaming that down because you can't even make use of it. So we then discard it in orbit itself. There's a few other novel things we can do, but it's very rudimentary, to be honest. I think you can, for example, count the number of ships you're seeing in a port. You can count the amount of cars that might be somewhere and things like that. So I think very rudimentary change detection, very rudimentary amount of object detection. I think you can do those kinds of things, but to be able to do things like the crop species identification or the yield prediction, etc., that we talked about, it does require a lot more compute than we can afford to do it in space, because it not only requires you to have more compute, it also requires you to have other kinds of data sets. Like, for example, for crop yield prediction, you need weather data and you need rainfall data and you need a bunch of these other data sets that you don't get while you're in orbit. So I think rudimentary levels of things are already being done, which is change detection and object detection. But then beyond that, there still remains to be seen what can be done. And we are experimenting. There are other companies experimenting with it. It'll get better as you get more compute for efficiency. But right now, on ground graphic cards and GPUs are designed for more power and more compute than figuring out power or power efficiency.
Yeah, that makes a lot of sense. Okay, so taking a step back, where six years in, where are you guys now? Sort of how many satellites are in space? Where do you actually want to get to? How many satellites do you want to ultimately have that makes sense on the hyperspectral business case? Then that other side of the business that you mentioned was a thought from the beginning, actually building, well, spacecraft basically. What's the thought on that? Where's that? Where's that going?
Yeah, so I would say we have launched 9 satellites in total till date. 3 of them were demonstration or Pathfinder satellites that went up in 2021 and 2022. And then we launched 6 Firefly commercial satellites this year, which are currently up there operating. So the 3 demos did their job. They proved hyperspectral as a concept was possible, that we could build hyperspectral cameras, beam down data, did pilots, then came down and deorbited and burnt up in atmosphere. So that was the 3 that we launched in 21 and 22. And in 25, in January, we launched 3 satellites, and then in August, we launched 3 more satellites. So 6 was going to be our phase 1, because phase 1 provided daily revisit anywhere on the globe, which means with these 6 satellites, we could come back and relook and revisit any point on the Earth every 24 hours. So if I'm taking an image at 10 a.m. today for Zurich, we can come back and look at it exactly 24 hours later. And then that holds true for any point on the globe. The plan is to have at least 18 hyperspectral satellites over the next couple of years. They will be a combination of fireflies and honeybees. So, there will be a combination of the current ones that are up there and then the new honeybees, which expand the wavelength range that we just sort of talked about. And those 12 additional satellites will go up either end of next year in 2026 or sometime in the first half of 2027, split across multiple launches. So that's kind of what we are looking for in terms of the expansion. We also have gotten now into the business of building satellites for other organizations. We're working with the Indian Air Force, we're working with a few other organizations where the expertise we have of building satellites for our own purposes, we can just take the same satellite platforms, put other kinds of cameras on them and deliver it to someone else. So it's already expanded beyond just hyperspectral because we had the capability. At some point, maybe in 5 years, we will work with space agencies to build some interplanetary exploratory missions for much cheaper than they could do their own scientific missions. But we are not focused on that today. That's a good to have, and that's a thing that will happen. But we want to ensure that our core business of providing insights and planetary intelligence for Earth-based organizations is taken care of, and it's running as a well-oiled machine before we sort of look at beyond the Earth. So right now, looking at the Earth, probably within the next 5 years, we'll start looking at the moon and Mars, and then let's see where we go from there.
And do you see yourselves also going maybe beyond hyperspectral sensors? Like there could be something else?
So we won a contract from the Indian government to build India's national Earth observation constellation. We already work with NASA in the US and NRO and NGA and so on for providing hyperspectral data already. That's globally. So that was the wedge. That was what made us unique. Now with the contract win in India to build India's national EO constellation, we are going to be building very high resolution satellites, submetric resolution, SAR satellites, and wide swath multispectral as well, mainly because that came as part of that contract. And, we know that there'll be customers here, so we can build it
Yeah.
and then provide that as additional offerings alongside our hyperspectral. So hyperspectral will always be our star data set. Every other data set will be complementary and augmented to make sure that we can see things together that a single satellite image can't.
And if you zoomed out a little bit, pun intended, from Pixxel to the wider EO sector, do you have sort of like a feel or a view where this might all go in the next few years, right? Because it could go many different ways. It could be like there'll be even more sensor types that we not really that are not very prevalent or that we're not even thinking about, or it could be just like more pervasive coverage, or it could be even higher resolution via bigger telescopes, or I don't know, this could go many ways, right? Do you have a view where this all goes?
I think it'll be both of those. I think we will see an increase in number of existing type of satellites. I think we are still woefully understaffed on very high resolution satellites. Right? Most of the capacity is bought out by defense and intelligence organizations, and there's only a few countries that have constellations. Maxar with its Legion satellites, I think they have 4 up there now. They probably need to launch 2 more. You have Airbus with their Pleiades constellation, and we have a few others, but there still aren't, enough. So one, you will see a lot more sovereign nations trying to build and launch their own high resolution satellites and SAR satellites and hyperspectral satellites. So we'll start to see this proliferation where not only you have some private organizations owning these constellations and providing data, you will see many countries starting to buy these satellites so they can operate it on their own as well. So the number will go on. And you're also right that we will start to see other kinds of modalities, right? Hyperspectral is new today. Maybe in 5 years or 6 years, we will see ultraspectral become a little bit more of the norm, and we hopefully will be there at the forefront of that. We will start to see a lot more of thermal imagery. Not much of that comes down today, and there are constellations like Constel IR and many others trying to do thermal imaging as well. Then you have X-band SAR that's already very prevalent, but what about C-band SAR and P-band SAR and the other things that helps penetrate foliage and other things? So I think you will see many more types as well as the number increases. But I think it won't ever be as many as Starlink. I don't think we will see tens of thousands of satellites. Maybe we will see close to 5,000, 6,000 EO satellites. Today, they're probably less than 1,000 maybe that are sort of active providing data. So I think that's one. And then, but most of the utility will actually be with the analysis now, with LLMs and artificial intelligence being what it is. What will be useful is how you can take these multiple data sets and extract insights.
That's actually a great segue to another question I want to ask you on the industry. So, how vertically integrated do you think a EO company should be? And vertically integrated, I don't mean now on the spacecraft production because we already talked about it. I mean, sort of like, should every EO company, like it seems to be the case right now, also do their own data analysis? Or, yeah, what do you think?
Yeah, so I think it's a very hard question to answer. There's no clean answer. Look, I would love to be a purist and say that, look, we will not get into analytics at all because some of our customers do that. But it's not as clean cut as that, right? So we will, in geographies and industries where we have partners who are doing their own analysis, we absolutely partner with them and we don't try to replicate that because there's no point reinventing the wheel. But there are just so many more other geographies where there don't exist companies like that. There don't exist any expertise on how to analyze this data. That's where having our own platform becomes really important, because I'm not gonna, as a company, be like, we will only provide data and we will see how quickly the market comes up and how many of these startups can actually analyze it. Whereas we could be selling and making this data a lot more available to organizations that need analysis along with data. So we will do both. We will do both where we have partners, we will work with partners, get out of their way, provide data. But there's just so many more use cases where we will actually need to do the analysis because we know how that hyperspectral data is. No one else is coming in to step in that gap in the near future. So I think companies honestly have to do both. You will see that with Planet Labs, you'll see that with Maxar, you will see that with SAR companies as well. Where we can provide data and get out of the way, we will do that so that we can sell more data to many more organizations. Where we can't, we will roll up our sleeves, get deep down, and provide the analytics. Because in the end, what matters is how many customers get the insight they want, not that we are sticking to a principle that will only sell data or analytics.
So, I mean, zooming out from that, you were talking at the very beginning how you basically like, found the gap and that's why you started what you're doing at Pixxel. Now with your very intimate knowledge of the EO ecosystem, do you see any sort of interesting gap. And it really could be anything. It could be like a sensor type, it could be some regional coverage, it could be like an analysis capability, it could be, I don't know. Some people get very excited about VLEO and think we should have a lot of VLEO satellites. Is there any gaps you see that are interesting?
I think VLEO is absolutely an untamed problem. The companies like Abido trying to sort of tame that with the recent launch that they did, and there's Earth Observant and a few others. So I would absolutely say I think that's an unconquered, that's the wild west of the space right now, and it is challenging, very challenging, because the more closer you get to Earth, the more the vibrations and the stability starts to get affected, which is important for imaging. But it is fundamentally not an unsolvable problem. At some point, we will also want to deploy our own cameras in VLEO platforms, and that's because it provides much higher resolution without having to build larger cameras or more expensive cameras, right? Absolutely. And I think we will also start to see a little bit more proliferation of geostationary imaging satellites. Right now, the resolution you can get from those is 200 meters or 100 meters and so on, which is not good enough. But that's where I think something like a Starship will become important. If you can build like a really huge telescope and put it in geo, maybe you can get to 10 meters or 5 meters from geostationary as well, which means persistent coverage over an area at a resolution that really start to sort of make sense as well. You will see a lot more weather companies also doing it, like tomorrow.io and so on. So I would say I think the biggest greenfield opportunity is probably VLEO. You already mentioned that, but I think the next big ones are what can enable EO to really take off. You'll have companies like medium Earth orbit relay satellites. I think the biggest problem is you have to wait 90 minutes for the data to come down. How do you
Mm.
make it instantaneous? You have that by having a relay satellite constellation that you can connect with 24/7. And so it's like an internet for satellites in space. Starlink is also opening up its communication terminals where you might be able to connect to the ground 24/7. So I think all those things will really start to unlock the value for imaging, because now you've taken an image and you've real time gotten it rather than 90 minutes later or 60 minutes later. And that all will mean more customers, more revenue, more experimentations.
Okay, cool. Well, I haven't thought about the EO from Geo, but I guess it makes sense because you're saying it's basically infinite temporal solution. You literally look at
Yeah.
one place all the time, which I guess is why a lot of spy satellites allegedly are up there because you kind of stay above
Yeah,
the
but they
missiles
still don't
flying
have the
over or something like
resolution.
that.
Yeah, yeah. I think they are there, some of them, but the resolution is not good enough for what they need, and that's where the larger satellites that Starship could enable will come into the picture. Yeah.
Yeah, very interesting. Okay, since we only have a few minutes left, let's go back to the beginning, or sort of back to the beginning, sort of like 6 years on, I guess. Because I think we have many sort of like budding entrepreneurs listening to this podcast as well. Like, sort of, what are some of your big generalizable lessons? So not something that's too specific to Pixel, but sort of, if there's something you learned over the last 5, 6 years that you think is useful for the entrepreneurs.
I think, probably that a lot of things that seem impossible when you start, like the people in the industry have seen a lot of things over the last couple of decades. And it starts to jade your minds into thinking that, okay, this is the best that's possible. This is the limit of what can be done in space because we are limited by not only the confines of space, but also the other trade-offs. But I've realized, I think that if you really start from a very ambitious set of requirements at the beginning and don't compromise on them at first go, and you try to push yourself and the team into brainstorming novel ways in which you can achieve that. Like 5 meters, when we decided we want to do 5 meters in 2020, was unheard of at that point in time. People thought, yeah, you're not going to get to 5 meters, maybe 10 meters or 20 meters, the best you can get. You're going to have all these problems with SNR and all of that. We launched 5 meter satellites this year, and they work, and they are being sold to customers, and customers are paying for them. We wouldn't have gotten there this year if we hadn't decided 4 years ago that 5 meters is really where we're going to set the absolute low bar at and then work from there. Now we are looking at similarly ambitious targets for the next 3 years and 4 years and 5 years. So I think many times the industry itself gets defeated by a lack of being ambitious at the beginning. Like it's kind of like that quote where you say you aim for the moon and it's okay if you miss because you'll end up in the stars. And very similar thing happened where we said let's aim at it and we'll see where we end up. And many companies I still see doing the same thing, that hey, this is has been tried before, it's not going to be possible because of XYZ reasons, but there's always ABC reasons how you can kind of surmount that as long as physics allows it. I think that's a big lesson I have learned personally. Always push for higher results, and you might not hit the same amount of results, but you will end up much better than where you would have been if you were realistic in the first place, right? So I think that's one.
Yeah.
The other one is probably maybe borrowing a phrase from Dune. Fear is a mind killer. I think most things is a lack of courage, a courage to sort of try something and be okay with it failing a little bit, the courage to call out things as they are and sort of call out people who have been more experienced in the industry, ask them questions. I think enabling environment where people can really question on the assumptions, question on the results, and question each other, and not be afraid of just trying things out and getting to a solution, I think plays a big psychological, pathway into really building things that you've previously not built before. So I would say probably those two things.
And those two are great. And just to state the obvious, those are not limited to space. They're just generally true in the
Right.
entrepreneurial journey, I think. Another sort of similar question is if you were leaving school today rather than 2019, like what do you think would excite you today? Other than like you're not allowed to say Pixxel the same thing, like Hyperspectral.
No, I don't think today Pixxel or Hyperspectral would be a very good bet because there are companies already doing it.
Yeah.
When it started in 2019, no one was.
Yeah.
I would probably say VLEO imaging. Albedo try to do it, and they still have a satellite sort of that's up there that's coming down in orbit, etc. But it's still an unsolved problem. There's so many things you can do, and if you can really figure out a platform where you can do 10 centimeter imaging, panchromatic or RGB, or where you can do sub 1 meter hyperspectral imaging, that starts to become like VLEO will unlock use cases for many things. The platform that you build is not only for imaging but for many other things. So I'd probably say that one. Either that or people still haven't figured out how do you take LLMs and really build a foundational model for Earth observation data where it's so easy and ubiquitous that ChatGPT is or Claude is for text and video and image. I think there's some scope there as well. So I think it's probably one of these two things.
Okay, great. Last couple of questions. So you're originally Pixxel yourself from India. I already mentioned like I'm very excited about the Indian space ecosystem. What's your sort of current view of the Indian space ecosystem?
Very exciting times to be here. I think the policy only came out last year. The Space Act or the bill will come out probably next year and so on. But there's all the right ingredients for a takeoff, pun intended. China in 2014, 2015 was sort of nowhere in the conversation with regards to where the private space industry is. Now they're probably second or maybe third. You can make the case for second just behind US. I think India is probably where China was in 2016, 2017. And if even a fraction of the companies today is kind of work out. One, it provides India with indigenous capabilities without so that they can rely on companies within India without having to depend on foreign sources for components, for satellites, for launches, and so on. And second, I think we will start to see companies where they're not only selling in India for India, but selling from India to the world, where the launch cost, ISRO used to be the cheapest launch vehicle provider for a long while until SpaceX came along. Probably time to take that mantle back with a few launch companies sort of doing what they're doing and so on. But we are still 10 years behind, I would say, US, and it really will take a lot of effort to catch up. So young days, which means a lot of companies and a lot of opportunities today. But I would say in 10 years, we will likely see with the trajectory catching up to China and sort of then trying to get close to where the US is. But for that, you will require launch companies and imaging companies and comm companies and everything to come together.
Yeah, and I mean the ISRO part continues super exciting as well for me. Like the plans for the like a crewed launch,
That's right.
moon, space station. It's kind of like you were just said. It's so ambitious, but it's good to shoot like set the bar that high because I actually really think a lot of that stuff will happen. That's
Yeah,
great.
absolutely. Yeah.
Final question, always the same. Science fiction. I mean, you already mentioned Dune. Like, is there any other sort of like favorites you want to point out?
Oh yeah, many. I would probably say Blind Sight by Peter Watts. That's a very unique take on, without spoiling anything, extraterrestrial intelligence and a very interesting story as well, the way that it sort of plays out. So Blind Sight is one. Project Hail Mary. There's recently a trailer that came out with Ryan Gosling, but when it came out, I think the book 3 years ago, I read through it in one sitting and just wonderful, exciting book to dive in. I would also probably say The Dispossessed by Ursula K. Le Guin. It's about, how divergent societies looking at different political orders can sort of diverge so widely and how science can try to sort of bring it back together because there's kind of just like a fundamental objective truth to science, but even that gets kind of warped by politics. I would say these three come to mind right now, but I'm sure there's many more.
These are all great, and I think apart from Project Hail Mary, the other two haven't been mentioned yet, those are great additions. So thank you very much for that. Awais, thanks so much for doing this. Best of luck with Pixxel over the next few years. It's very exciting what you guys are doing. So yeah.
Thank you. Thanks for having me, Rafal. Great to be here.
Thank you.
And that's it for another nominal episode of the Space Business Podcast. And once more, if you enjoyed this episode, please leave us a 5-star rating on your favorite podcast platform, such as Apple or Spotify. You can follow us on Twitter at podcast_space. We're also on LinkedIn, under the Space Business Podcast. Lastly, if you have any feedback, including ideas for guests, and that may even include yourself if you have an exciting space story to tell, or are interested in becoming a sponsor, or really for any other suggestions, you can drop us an email at spacebusinesspodcast@gmail.com. Thanks so much for listening, and see you for the next episode.